Hello, in this video we're going to be doing a flow rate problem, and we're also going to be looking at something new, an energy balance. Okay, so let's look at our problem. We're told that a large body of water is being transferred through a 10 centimeter inner diameter pipe at a rate of 62,000 liters per hour to a second location that is 31 meters lower in elevation. If the inner diameter of the piping at the lower elevation is half the initial inner diameter, calculate the initial and final linear velocities of the fluid, and this is going to be in meters per second. And for the second part, we're told that we have a turbine and generator set up at the lower location, and if they operate with 93% efficiency, we want to find out what the power output is in kilowatts. Alright, so just to make a brief little visual, we have our body of water up here, and then we have piping going down in elevation, 31 meters to be exact. That's our Z value for the height. And then the piping at the beginning, the initial diameter is 10 centimeters, and at the end it gets a little more narrow, and the final diameter is 5 centimeters because we were told that it's half of the initial inner diameter. Okay, and we have all the water up here. It's going to be flowing through here, and we also have our turbine set up right there. And to get started on this problem, we just have to know that the initial volumetric flow rate is equal to the final volumetric flow rate. Alright, so because the initial and final volumetric flow rate, because they have to be the same, that means that when we're going from a large diameter to a small diameter, for that volumetric flow rate to stay the same, the linear velocity has to be speeding up quite a bit for the volumetric flow rate to be the same. And if we break that down, the initial volumetric flow rate is going to be equal to the initial linear velocity multiplied by the cross-sectional area right here. Okay, and if we rewrite our initial volumetric flow rate in the correct units, we'll take our 62,000 liters per hour, and we want the time in seconds, and then let's get it into meters cubed. And I get an initial volumetric flow rate of 0.01722 meters cubed per second. Alright, and we're going to be using that in just a second. And we also need to know the initial area. That's going to be pi r squared, or pi initial diameter squared over 4. And then when we put this in the right units, we'll get that our initial area is 0.00784 meters squared. Okay, and now to find our initial linear velocity, we'll take these two values here, manipulate this relationship right here, and we have that the initial linear velocity is the initial volumetric flow rate over the initial area, and that's going to be equal to 2.193. Alright, let's write that with our units and box it. Okay, and we're going to do the same exact thing for the final linear velocity, because the volumetric flow rate in initial equals the volumetric flow rate final. We can do the same exact thing again and get our final linear velocity by taking the volumetric flow rate and dividing it by the final area. Alright, but before we can get our final linear velocity, we're going to have to calculate our final area with our final diameter. Okay, and that's just going to be pi d final squared over 4. And putting it in the right units, I get that our final cross-sectional area is 0.001963 meters squared. Okay, and now we have enough information to get our final linear velocity. Just going to be the volumetric flow rate divided by the cross-sectional area that we just found. And then the final linear velocity of the fluid is 8.772 meters per second. Okay, and before we can do our energy balance, we're going to need one more thing, and that's the mass flow rate, and we're going to want that in kilograms per second. Okay, and that's equal to the volumetric flow rate multiplied by the density of water. So we have our 0.01722 meters cubed per second multiplied by the density of water, and one of the common values is 1,000 kilograms per meter cubed, and then we get that the mass flow rate is 17.22 kilograms per second. And we'll use that in the calculation on the next page where we do an energy balance. Alright, so let's get started with that energy balance. So we have our initial potential energy because the elevation of 31 meters, and then we also have our initial kinetic energy, and for the second point we have our final kinetic energy, and we're assuming because we're starting at an elevated position and going to a lower elevation that we're going to have leftover energy. And usually what people do is they don't want to just leave that lying around, so they'll attach a turbine, as we've shown here in our original figure right here, and this will harvest and capture the leftover energy from the water that we had up here. Okay, and each of these energy variables can be broken down into its components. So for potential, that's the mass flow rate times gravity times the height. For the initial kinetic energy, that's 1/2 mass flow rate initial velocity squared. And then for final kinetic energy, that's 1/2 times the mass flow rate times the final velocity squared. And then we'll just leave our ET right here for the energy of the turbine. And a common thing you'll see people do in these energy balances is they'll divide out the mass flow rate. So that'll just be gz plus 1/2 initial velocity squared equals 1/2 of the final velocity squared plus our power output of the turbine, and we're going to divide that by the mass flow rate. And then what we ultimately want to do is solve for this. And this right here is assuming that it's 100% efficient. We haven't factored in that it's only 93% efficient. All right, and this is what we get once we isolate the energy of the turbine. And from here, we just have to simply plug in all the appropriate values. And we don't have to include the units because we know that we'll get the answer in joules per second or watts if the mass flow rate is kilograms per second, the gravity is meters per second squared, the height is in meters, and so on. Alright, so doing these calculations, we get 4,610.321 joules per second. But we have to factor in the 93% efficiency, so we're only going to get 0.93 of the original calculation. And we also want this in kilowatts, so we're going to multiply by the 0.93, and then we're also going to do the division of 1,000, and then we'll get our final answer for the power output of the turbine generator system is 4.288 kilowatts. Okay, thanks for watching. I hope you found this helpful.